Tomorrow has already happened to you, not in some vague poetic sense, not as metaphor. According to one of the most carefully tested theories in the history of physics, there exist paths through the fabric of reality along which tomorrow bends backward and becomes yesterday. Paths where a traveller moves steadily forward through their own experience, eating breakfast, watching light shift across a wall, breathing in and breathing out, and yet arrives, without ever turning around, at a moment they have already lived. These paths have a name. Physicists call them closed time-like curves. They were first discovered not by a physicist at all, but by a logician named Kurt Gödel, who in 1949 handed his solution to Albert Einstein as something between a birthday present and a philosophical challenge. The equations were flawless, the implication was staggering, and tonight we are going to follow that implication, gently, slowly, to see where it leads. Not to answers necessarily, certainly not to machines or devices or the furniture of science fiction, but to something quieter, something that might, by the end, feel less like strangeness and more like stillness. Because the deepest question hidden inside a closed time-like curve is not whether you could travel to the past. It is whether the difference between past and future was ever as solid as it seemed. So let yourself settle. Let the weight of the day begin to thin. We are going somewhere unusual tonight. Somewhere that curves. Somewhere that, perhaps, you have already been. There is a way to think about your life as a line. Not drawn on paper, but drawn through the very structure of reality. Through something physicists call spacetime. Every moment you experience, every heartbeat, every slow blink of your eyes, traces a path. That path is called your world line. It stretches behind you into the moments that have passed and ahead of you into the moments that have not yet arrived. For most of us, for most of the universe as we understand it, these world lines move in one direction. They extend forward. They do not loop. They do not curve back. But the mathematics of general relativity, Einstein's own framework for understanding gravity, space, and time, permits something deeply unusual. Under certain extreme conditions, a world line can bend, not just slightly, not just into a gentle arc. It can curve so thoroughly that it returns to the very event where it began. This is a closed time-like curve. The word closed means the path forms a loop. Time-like means that along this path, time passes normally for whatever is traveling it. You would age, you would think, you would feel the continuity of your own experience, moment after moment, sensation after sensation, and yet the geometry of the path itself would deliver you back to a point in your own past. This is not a wormhole. It is not a machine. It is a property of the shape of space-time, a geometric possibility woven into the equations that describe how mass and energy curve the universe around them. To understand how such a curve can exist, it helps to picture something simpler. Imagine a cone of light expanding outward from a single event, the moment you snap your fingers perhaps. That cone represents every direction a beam of light could travel from that snap. In flat, ordinary spacetime, the cone stays upright and symmetrical. But near immense gravitational fields, near objects of extraordinary density or rotation, the cone begins to tilt. It tips, and if it tips far enough, something remarkable happens. The future direction of the cone points partially into what we would normally call the past. A path that follows this tilted cone, a path that moves forward through time as experienced locally, can nonetheless curve through the larger geometry and arrive at an earlier moment. No one built anything. No one activated a device. The shape of space-time itself created a passage, and that passage, quiet and mathematical and strange, is what we call a closed time-like curve. In the autumn of 1949, two elderly men could often be seen walking together along the quiet streets of Princeton, New Jersey. One was Albert Einstein, by then in the final years of his life, his great work behind him. The other was Kurt Gödel, an Austrian logician who had already shaken the foundations of mathematics with his incompleteness theorems, proofs that showed certain truths in mathematics can never be proven within the system that contains them. They were close friends, unlikely as the pairing seemed. Einstein once remarked that in his later years he went to his office at the Institute for Advanced Study mainly for the privilege of walking home with Gödel. Their conversations ranged widely, but one thread kept returning: the nature of time. Einstein's own theory of general relativity had revealed that time was not absolute, not a universal clock ticking identically for everyone. Time bent near massive objects. Time stretched at high velocities. But even Einstein seemed to assume that time, however flexible, still flowed, that the present moment advanced, that the past was gone and the future was yet to come. Gödel was not so sure. For Einstein's 70th birthday, Gödel offered him something unusual, not a watch or a book, but a new exact solution to Einstein's own field equations. An exact solution is not an approximation. It is a mathematically precise description of a universe that is fully consistent with general relativity. And Gödel's solution described a universe in which every point, every location, every moment contained a closed time-like curve, a universe where time, followed far enough, always came back to itself. Gödel did not present this as engineering. He was not interested in building anything. He was making a philosophical argument. If Einstein's equations, the most rigorously tested description of gravity and spacetime ever devised, permitted a universe where time loops, then perhaps the flowing quality of time, the sense that the present moves forward, was not a feature of reality at all. Perhaps it was something else, an appearance, a feeling generated by minds embedded within a structure they could not see from outside. Gödel was using Einstein's own theory to suggest that time as we experience it might be an illusion, and the mathematics, Einstein had to admit, was impeccable. The gift was also a challenge, and it remains unanswered. To picture what Gödel actually proposed, you have to let go of something familiar. When we say the word rotation, we usually mean an object turning, a wheel, a planet, a dancer. Something spins relative to the space around it. But Gödel's universe does not contain objects spinning within a fixed background. In his solution, everything rotates. The matter in the universe and the space-time that holds it are co-rotating together, like water swirling in a bowl, where the bowl itself is also turning. There is no still point, no fixed reference frame against which the rotation can be measured from within. An observer living inside such a universe would not feel dizzy. They would not detect any centrifugal force or sense that the cosmos was spinning. They would simply live their lives, see stars, measure distances, and experience time, all seemingly normal. Yet the geometry beneath their experience would be quietly doing something extraordinary, because when space-time itself rotates, it drags the structure of cause and effect along with it. Imagine the light cones we spoke of earlier, those expanding cones that represent the possible futures branching from any event. In Gödel's universe, the rotation of spacetime tilts every one of these cones, not dramatically at first, not in ways that a local observer could detect, but cumulatively across vast distances. The tilting adds up. Follow a path far enough from your starting point, tracing a wide arc through the rotating cosmos, and the tilted cones guide you along a trajectory that curves, slowly, steadily, back toward your own past. This is not a flaw in the mathematics. It is not an edge case or a trick. Gödel proved that in a universe with uniform rotation and a particular relationship between matter density and the cosmological constant, closed time-like curves thread through every single point. There is no safe zone, no region where time remains strictly linear. Everywhere the geometry permits return. Our own universe, as far as observations suggest, does not rotate in the way Gödel described. Measurements of the cosmic microwave background, that ancient light from the early universe, show no sign of large-scale rotation. But that was never quite Gödel's point. He was not claiming we live in his rotating cosmos. He was demonstrating that the laws of physics, as Einstein formulated them, do not require time to behave the way we assume. The equations allow loops, and if the equations allow them anywhere, Gödel believed, then the flowing nature of time cannot be fundamental. It must be something more local, more contingent, more fragile than we imagined. There is a phenomenon in our own universe, not in Gödel's theoretical one, but in the real, observable cosmos, that hints at how space-time can be twisted by the things it contains. It is called frame dragging, and it happens to some small degree right here near Earth. The idea is deceptively simple. When a massive object rotates, it does not merely spin within space-time the way a ball spins in air. It pulls the space-time around it into motion, not metaphorically. The actual geometric structure of the region surrounding the object is dragged, twisted, carried slightly in the direction of the object's rotation. Imagine placing a heavy, spinning sphere in a pool of thick honey. The honey near the sphere would begin to swirl, drawn into motion by the surface dragging against it. Space-time behaves, in this limited analogy, like that honey, and this is not speculation. In 2011, after more than 40 years of development, a satellite called Gravity Probe B confirmed the effect with extraordinary precision. It measured how Earth's rotation, our modest, familiar planet, dragged the space-time around it by approximately 0.011 arcseconds per year. This is a vanishingly small amount, a fraction of a degree, and yet it was there, exactly as the equations predicted. The effect carries the name lens stirring, after the two physicists who first described it mathematically in 1918. Near Earth, it is barely detectable, but near objects far more massive and far more rapidly rotating, near neutron stars for example, or the supermassive objects at the centers of galaxies, the dragging becomes fierce. Space-time is not gently nudged, it is wrenched, pulled into spiraling configurations that would be unrecognizable to anyone accustomed to the calm geometry of our solar neighborhood. And this is where the connection to closed time-like curves begins to sharpen, because frame dragging, taken to its extreme, does not just twist space, it twists time. The distinction between spatial directions and temporal directions becomes blurred in the swirling geometry near a rapidly rotating massive body. The like cones, those markers of what is future and what is past, begin to tip, just as they do in Gödel's solution, but now not because the entire universe rotates. Instead, a single object, by its mass and spin, creates a local region where the geometry permits the same kind of curving return. Frame dragging is the bridge between theory and astrophysics. It is the whisper, detected even here around our own gentle Earth, of a deeper possibility that wherever mass spins, space-time follows, and where space-time follows far enough, time itself may learn to close. In 1963, a New Zealand mathematician named Roy Kerr accomplished something that had eluded physicists for nearly half a century. He found an exact solution to Einstein's field equations describing a rotating black hole. Until Kerr's work, the only well-understood black hole solution was the Schwarzschild solution, which described a perfectly still, non-rotating black hole, an object that, while mathematically elegant, does not truly exist in nature. Real black holes rotate. They form from the collapse of spinning stars, and as they shrink, their rotation accelerates, the way a figure skater spins faster when drawing in their arms. Kerr's solution captured this rotation, and in doing so it revealed a structure far stranger than anyone had expected. A non-rotating black hole has a point-like singularity at its center, a place where density becomes infinite and the known laws of physics cease to function. But a rotating black hole, a Kerr black hole, has a singularity shaped like a ring, a circle of infinite curvature spinning in the dragged spacetime, surrounded by layers of geometric strangeness, and within those layers, beyond what is called the inner Cauchy horizon, the mathematics produces something that should by now feel familiar. Closed time-like curves. They emerge not as something inserted into the solution, not as an artificial addition, but as a natural consequence of the geometry. The rotation of the black hole drags space-time so severely in this inner region that the future direction of time, as defined by the tilting of light cones, curves back upon itself. A path that moves continuously forward through local time can, in this region, complete a loop and return to an event it has already passed through. What makes this particularly striking is how common rotating black holes appear to be. Observations suggest that most, perhaps nearly all, of the black holes in the universe carry significant angular momentum. The supermassive black hole at the center of our own galaxy, Sagittarius A star, rotates. The stellar mass black holes detected through gravitational wave observations rotate. Rotation is not the exception, it is the norm. And every one of these rotating black holes, if Kerr's mathematics is to be trusted all the way inward, contains a region where closed time-like curves exist. Whether anything could survive passage to that region is another question entirely. The gravitational forces, the radiation, the instability of the inner horizon, all of these present barriers that may be physically impassable, but the geometry is there, quietly. In every spinning remnant of a collapsed star, the mathematics whispers the same possibility. Time here can close. Beyond the interiors of rotating black holes, physicists have imagined other structures that might coax spacetime into closing upon itself. Two of the most discussed are Frank Tipler's rotating cylinder and the traversable wormhole proposed by Kip Thorne and Michael Morris. Neither exists. Neither may ever exist. But both are honest solutions to the equations of general relativity, and each illuminates a different facet of what it takes to bend time into a loop. Tipler's proposal, published in 1974, asks you to imagine a cylinder of immense density, infinitely long, rotating at tremendous speed. As the cylinder spins, it drags spacetime around it, the same frame-dragging effect we encountered near Earth, but amplified to an almost unimaginable degree. Near such a cylinder, the dragging would be so severe that a traveller following a carefully chosen path around it could trace a world line that closes on itself. They could return to their own past. The infinite length is a problem, of course. An infinite object cannot be built. Tipler himself acknowledged this, but the solution is mathematically valid, and what it reveals is important. It is not mass alone that creates the conditions for a closed time-like curve. It is mass and motion together. The spinning is essential. Without rotation, the cylinder does nothing unusual. With it, time itself begins to spiral. The Morris-Thorne wormhole operates by a different principle. Rather than dragging spacetime through rotation, it connects two distant regions of spacetime through a short tunnel, a bridge through the geometry itself. In its simplest form, a wormhole is merely a shortcut through space. But Thorne and his colleagues realized that if one mouth of the wormhole were moved at high speed relative to the other, or placed in a stronger gravitational field, time dilation would cause the two mouths to age differently. Enter through one mouth, and you might emerge from the other at an earlier time. The wormhole would become, in effect, a closed time-like curve generator. The catch, and it is a significant one, is that holding a wormhole open requires something called exotic matter, a substance with negative energy density. Whether such matter can exist in the quantities needed is one of the deepest open questions in physics. The Casimir effect demonstrates that negative energy density is real at quantum scales, between two closely placed metal plates. But the leap from quantum scale effects to a traversable tunnel through spacetime is almost incomprehensibly vast. So we are left at the close of this chapter with a peculiar tension. The mathematics of general relativity, our best and most thoroughly tested theory of gravity, permits closed time-like curves in multiple distinct scenarios, rotating universes, spinning black holes, hypothetical cylinders, theoretical tunnels. The permission is broad and robust, but the engineering is, for now and perhaps forever, beyond reach. The equations say yes. The universe so far remains quiet on the question of how. Suppose for a moment that a closed time-like curve exists and that you can traverse it. Suppose you follow that curving path through space-time and arrive at a moment before you were born. You step out, if stepping is even the right word for something so geometrically strange, and there is the world, decades before your arrival in it. What happens next is where the trouble begins. The grandfather paradox, as it is traditionally framed, asks a pointed question. What if you prevent the events that led to your own existence? Not through malice necessarily, perhaps through accident, perhaps simply by being present where you should not yet be, altering the conditions that would eventually bring you into being. If you succeed, then you were never born. But if you were never born, you never traversed the closed time-like curve. And if you never traversed it, you never arrived in the past to change anything. Which means the events proceed as they originally did. Which means you are born. Which means you traverse the curve. Which means you arrive. And we are back where we started, caught in a contradiction that tightens with every pass. The usual response to this paradox is to treat it as a storytelling puzzle, a clever riddle designed for time travel films. But the paradox is more significant than its popular framing suggests. What it actually exposes is not a problem with time travel. It is a problem with causality. Our entire framework for understanding the world rests on the assumption that causes precede effects. Every scientific experiment, every legal argument, every diagnosis a doctor makes, all of it depends on the idea that what happens first determines what happens next. The grandfather paradox reveals that this assumption is not a proven law. It is a principle that holds within a particular geometry of spacetime, one in which world lines do not close. Introduce a CTC, and the chain of cause and effect is no longer a chain, it becomes a circle, and in a circle the question what caused what loses its anchor. The paradox, then, is not merely a thought experiment about visiting the past. It is a diagnostic tool that reveals something usually invisible, the deep and largely unexamined assumption that underlies everything we think we understand about how events relate to one another. If time can loop, that assumption trembles. Not necessarily breaks, but trembles. The grandfather paradox assumes something that seems obvious but may not be true, that a person traveling along a closed time-like curve would be free to do anything upon arriving in the past, free to interfere, free to disrupt, free to set in motion events that contradict their own existence. But in 1983, the Russian physicist Igor Novikov proposed a different possibility, one that is strange, elegant, and deeply unsettling in its own quiet way. Novikov's self-consistency principle suggests that in any region of spacetime containing a closed time-like curve, only self-consistent sequences of events are physically possible, not just likely, not just preferred. The only events that can occur are those that do not create contradictions. Think of it this way: the laws of physics, electromagnetism, gravity, thermodynamics already constrain what can happen. You cannot walk through a wall, not because some rule forbids it in the abstract, but because the electromagnetic forces between atoms make it physically impossible. Novikov's principle extends this idea to time. In a CTC region, the laws of physics themselves would constrain events so that no paradox ever forms. If you traveled to the past, you would find yourself unable, not by willpower or moral restraint, but by the physics of the situation, to do anything that contradicts the history that already includes your arrival. A gun would jam, a step would falter, circumstances would conspire, naturally and without any sense of conspiracy, to ensure that everything remains consistent. You might want to change the past. You might try, but every attempt would, by the structure of physical law, fold into a sequence that was already consistent. The grandfather paradox dissolves, not because time travel is impossible, but because paradoxical time travel is impossible. Some find this comforting. The universe protects its own logic, but others find in Novikov's principle something perhaps more disquieting than the paradox it resolves. Because what the principle describes is a world in which the outcome of every event in a CTC region is already settled, determined, closed, not by fate in any mystical sense, but by the geometry of the loop and the constraints of physical law. You are free to act. You are not free to contradict. The line between those two freedoms may be thinner than it first appears. There is another paradox that lives inside closed time-like curves, one that involves no contradiction at all, and yet disturbs something even deeper than logic. It is sometimes called the bootstrap paradox, and it goes something like this. Imagine a traveler on a closed time-like curve who carries with them a beautiful, intricate watch. Upon arriving in the past, they hand the watch to a younger version of themselves. That younger self carries the watch through the years, aging alongside it, until the moment comes when they enter the closed time-like curve and travel to the past, carrying the watch. They hand it to their younger self, and the loop continues. The question that surfaces is disarmingly simple. Where did the watch come from? No one ever built it. No craftsman ever assembled its gears. No designer ever conceived of its face. It exists within the loop, passed from hand to hand across the curve, aging and yet persisting, but at no point in its history was it created. It has always existed within the loop, and the loop has always contained it. Nothing contradicts. The watch does not generate a logical paradox. The younger self receives it, the older self gives it. The timeline is perfectly consistent. Novikov would have no objection, and yet something feels wrong, deeply, fundamentally wrong, because we carry within us an almost unshakable conviction that everything which exists must have been brought into existence, that every object, every piece of information, every melody and theorem and gesture has an origin, a moment when it first appeared. The bootstrap paradox challenges this conviction without contradicting any law of physics. It asks us to consider the possibility that existence does not require origin, that something can simply be without ever having been made. This is not a familiar kind of discomfort. The grandfather paradox threatens logic. It produces a contradiction, and contradictions are things we know how to reject. But the bootstrap paradox threatens something more personal. It threatens our sense that the universe is fundamentally a place where things come from somewhere, where causes produce effects and effects can always be traced back to causes. In a closed time-like curve, that tracing back eventually leads you in a circle, and in the center of that circle the watch sits, beautiful, unexplained and uncreated. Let us return to Novikov's self-consistency principle and sit with it a moment longer, because there is a dimension to it that extends beyond physics and into something that touches you more personally. Imagine that you are on a closed time-like curve. You do not know this, as we will explore later. There may be no way to know it from the inside. But the structure of your world line is closed. It loops, and according to Novikov, every event along your path is constrained to be self-consistent. Now consider what this means for your experience. You wake up, you make coffee, you choose, or feel that you choose, to wear a particular shirt. You speak words that feel spontaneous. You hesitate at a decision, weigh your options, and act. From inside, everything feels exactly like freedom. There is no visible hand guiding your choices, no sensation of being constrained. The deliberation is real, the uncertainty is real. The sense of openness, that you could have done otherwise, is vivid and present. And yet, if Novikov is correct, you could not have done otherwise. Not because something prevented you in any experiential sense, but because the only events that can occur on a closed time-like curve are those that form a self-consistent loop. The outcome was settled, not before you chose exactly, but in a way that your choice was always part of the outcome. This is a form of determinism, but it is unlike the cold, mechanical determinism that people usually imagine. It is warm. It feels like agency. You experience deliberation, uncertainty, resolution. All the internal textures of free will are present. Only the metaphysical status has shifted. You are not choosing the future. You are living a shape. Some philosophers call this compatibilism, the idea that free will and determinism are not actually in conflict, that feeling free is all that freedom ever was. Others find this inadequate, insisting that real freedom requires the genuine ability to have done otherwise. On a closed time-like curve, this debate is not abstract, it is the structure of your existence. Every thought, every impulse, every moment of apparent spontaneity is threaded into a loop that was always self-consistent. And the strangest part may be this: if Novikov is right, you would never notice. The consistency would feel, from every internal vantage point, exactly like choice. The loop does not imprison you, it simply is you. your actions, your experiences, your decisions, all woven into a shape that closes without contradiction. Freedom and constraint on a closed curve may be the same thing. Sometimes the most revealing thought experiments are the simplest. In 1991, Fernando Echeverria, Gunnar Klinkhammer, and Kip Thorne proposed one that strips away all the drama of grandfathers and watches and asks a basic physical question. Take a billiard ball, send it toward the mouth of a wormhole that functions as a closed time-like curve. The ball enters the wormhole, emerges in the past, and, here is the key detail, its past emerging self collides with its earlier self on the way in. At first glance, this seems to produce a contradiction. If the emerging ball knocks the entering ball off course, then the ball never enters the wormhole. But if it never enters, it never emerges to knock itself off course. We appear to be back in grandfather territory, but Echeverria, Klinkhammer, and Thorne discovered something remarkable. When they worked through the mathematics with care, they found not zero solutions, but infinitely many self-consistent solutions. The ball could glance off its other self at a slight angle, just enough to deflect its path, but not enough to prevent it from entering the wormhole. It could clip itself gently, altering its trajectory while still ensuring it entered the wormhole from a direction consistent with the collision it would later cause. The geometries of these solutions varied, but all of them obeyed Newton's laws, conserved momentum, and maintained perfect consistency. No paradox arose, not one. What arose instead was an abundance of possible histories, each internally coherent, each physically valid. The mathematics did not strain or break under the weight of a closed time-like curve. It flourished. It produced more self-consistent outcomes than an ordinary, non-looping scenario would. This result is quietly revolutionary. It suggests that self-consistency on a closed time-like curve is not a fragile, special condition that is difficult to satisfy. It is robust. The space of consistent solutions is vast, perhaps infinite. The universe, it seems, does not struggle to accommodate loops. It finds consistency easily, naturally, almost effortlessly. And each consistent solution describes a slightly different version of events, the ball deflecting at this angle rather than that, arriving at this moment rather than that. From the outside, these differences are subtle. From the inside, each would feel perfectly ordinary, just a billiard ball rolling, colliding, and continuing on its way. Nothing strange, nothing paradoxical, only the quiet, invisible structure of self-consistency, humming beneath the surface, allowing everything to proceed as though time had never curved at all. We began this chapter with a paradox about contradiction, the grandfather who cannot exist. We moved through a paradox about constraint, the loop that permits only consistency, and we paused at a paradox about objects, the watch that was never made. Now, as this chapter draws toward its close, consider one final layer. The deepest form of the bootstrap paradox involves not objects but information. Imagine a mathematician who, while traveling a closed time-like curve, receives a letter. Inside the letter is a complete, rigorous proof of a theorem she has been struggling with for years. The proof is elegant, it is correct, she studies it, memorizes it, and years later, upon entering the CTC, she writes the proof into a letter and sends it to her past self. The proof exists, it is valid, it works, but no one ever devised it. No mind ever moved from ignorance to insight. No creative act ever produced it. The proof simply is, circulating within the loop, teaching itself to its own discoverer, who then passes it along to become the discoverer once more. In ordinary experience, knowledge comes from somewhere. A scientist observes a pattern. A philosopher reasons through a chain of arguments. A child learns something new by touching the world and seeing what happens. We assume, deeply, almost reflexively, that every piece of knowledge was, at some point, generated, that there is always a first time, a moment of creation, an origin for understanding. The informational bootstrap paradox dissolves that assumption, not by contradicting it logically, but by presenting a scenario in which it simply does not apply. The proof has no first time, it was not generated. It circulates, intact, without origin, and this challenges not just our model of causality but our model of creation itself. How do new things come into being? We normally answer through causes, through processes, through the accumulation of smaller steps that lead to something that did not exist before. But on a closed time-like curve, the concept of before has lost its footing. There is no moment that is definitively first. The loop contains the proof, and the proof contains the loop, and the question of which came first has no answer, because first is not a concept that applies within a circle. Perhaps this is where we should leave causality for now, not shattered, not disproven, but gently loosened, still useful, still powerful. But perhaps in the presence of closed time-like curves, no longer the final word on how reality holds itself together, here is perhaps the most unsettling thought in this entire journey, and it arrives not with a dramatic flourish but with a quiet, almost disappointing simplicity. If you were on a closed time-like curve right now, if the world line your body traces through space-time happened to be one that curves back upon itself, you would not know. There would be no flicker, no shimmer at the edges of your vision, no strange hum beneath the ordinary sounds of your life. You would wake up tomorrow morning, pour water into a glass, feel the coolness of it against your palm, and think of the day ahead, and none of this would feel like a repetition, none of it would register as a return. Because from inside a closed time-like curve, time does not feel closed. It feels like time always feels, sequential, forward, one moment giving way to the next. Your memories would form in the usual direction. Each new experience would feel new. Each hour would seem to follow the last. The subjective texture of your life, the quality of experience that makes Tuesday feel like it comes after Monday, would be entirely intact. This is because a closed time-like curve does not reverse time for the person on it. It curves the geometry of space-time around a path that, from the traveler's own perspective, is always moving forward. Your internal clock, the biological, neurological, experiential clock that generates your sense of duration and sequence, would tick in its usual direction the entire way. You would never feel the curve, you would never perceive the closing. The loop, by its very nature, is invisible from within, and this is what makes closed time-like curves philosophically radical in a way that goes far beyond their mathematical strangeness. Most extraordinary claims in physics come with, at least in principle, a way to test them. But a closed time-like curve offers no internal signature, no observable difference from the inside between a looped life and a linear one. If you are living on a curve that closes, your experience is indistinguishable from the experience of someone living on a line that does not. The same memories, the same sense of progression, the same feeling of a future that has not yet arrived. This means the question of whether your world line is closed or open may be, in the most rigorous sense, unanswerable from where you sit. Not because the truth does not exist, but because the truth lives in the shape of space-time itself, a shape you cannot step outside of to observe. You are within the geometry, and from within, the loop feels exactly like a line. Long before physics raised questions about the structure of time, your brain was already making quiet editorial decisions about how to present temporal experience to your conscious mind. What you perceive as now, this seamless, continuous present moment, is not a direct readout of reality. It is a construction, a carefully assembled estimate, produced by neural processes that are themselves operating with significant delays and creative liberties. When light hits your retina, the signal takes time to travel along the optic nerve to the visual cortex. When sound enters your ear, it takes a different amount of time to be processed in the auditory cortex. Touch, proprioception, the chemical senses, each arrives at consciousness at its own pace, through its own pathways, with its own processing delays. Some of these delays are as long as 80 milliseconds. In the rapid-fire world of neural processing, 80 milliseconds is considerable. And yet, when you watch someone clap their hands, you perceive the sight and the sound as simultaneous. The brain waits, it gathers, it aligns. It constructs a unified moment from signals that did not, in physical reality, arrive together. This process is called temporal binding, and it is one of the most remarkable feats of neural engineering in the human body. But it does not stop there. The brain also engages in something neuroscientists call predictive coding, a process in which it generates expectations about what is about to happen and fills in perceptual gaps before incoming signals confirm or correct them. You do not merely react to the world, you are constantly, unconsciously generating a low-resolution draft of the immediate future and experiencing it as the present. This means that your sense of now is, in a very real neurological sense, a blend of the just past and the almost future, stitched together so smoothly that the seam is invisible. The present moment, as you experience it, is already a small fiction, a useful one, an elegant one, but a fiction nonetheless. It is the brain's best guess at what is happening, offered to consciousness with such confidence that you never think to question it. What does this mean for closed time-like curves? It means that the mechanism by which you experience time, the internal clock that generates your sense of sequence and duration, is already an interpretation, already a model, already something other than a direct perception of how time actually works. If you were on a closed time-like curve, your brain would receive the same sensory inputs, process them through the same predictive models, bind them together with the same temporal smoothing, and deliver to your consciousness the same seamless, forward-moving experience of time that it always does. The loop would not disrupt the construction, the curve would not introduce a glitch, because the sense of moving forward through time was never a measurement of space-time's actual structure. It was always the brain's own private clock, ticking in a rhythm that has more to do with neural architecture than with the geometry of the universe. And private clocks, by their nature, cannot tell you what the larger structure looks like. They can only tell you how it feels. Most people have felt it. You walk into a room, or hear a sentence, or catch the angle of light through a window, and something in you insists, quietly, almost shyly, that this has happened before. Not something like this. This exactly. The sensation is so vivid that for a moment you feel certain you could predict what will happen next. And then it dissolves. The certainty fades. You are left with only the faint residue of recognition and no memory to attach it to. This is déjà vu. It is one of the most common anomalous experiences reported by human beings. Studies suggest that somewhere between 60 and 70% of people experience it at least once, with younger adults and those prone to fatigue or stress reporting it more frequently. And while it feels like a mystery of the deepest kind, neuroscience has offered some gentle explanations. The leading hypothesis involves the temporal lobe, specifically the regions associated with memory encoding and familiarity detection. Under normal circumstances, when you encounter something you have experienced before, these regions fire together, one signaling that the situation is familiar, another retrieving the specific memory that explains why. Déjà vu, some researchers suggest, occurs when the familiarity signal fires without the accompanying memory retrieval. Your brain tells you this is known, but it cannot tell you how or when you knew it. The recognition arrives without a referent, a signal with no source. It is, in neurological terms, a misfiring, a glitch in the timing of two processes that usually operate in concert. And this explanation is well supported, grounded in studies of epilepsy patients whose temporal lobes, when electrically stimulated, produce déjà vu reliably and repeatedly. The science is solid. The mystery, in a clinical sense, is largely resolved. And yet, place this experience alongside what we have been exploring tonight, and something poetic stirs. Not a claim, not an argument, just a question that hangs in the air like a half-remembered melody. If you were on a closed time-like curve, if you had in some geometric sense already lived this moment, what would that experience feel like from the inside? You would not remember the previous pass, because the previous pass is this pass. Your brain would construct the same perceptions, bind them into the same seamless present, deliver the same sense of novelty. But what if, somewhere in the delicate machinery of temporal processing, a faint echo leaked through, not a full memory, not a replay, just a whisper of familiarity, a recognition without a source, a feeling that this has happened before. We cannot say and should not say that déjà vu is evidence of a closed timelike curve. That would be a leap far beyond what the science supports. But we can sit with the resonance between these two ideas, the neurological and the geometric, and notice how strangely well they rhyme. A feeling of return, arising from a brain that may or may not be on a path that returns. There is no proof here, only a question that feels, for a moment, like it already knows the answer. There is a ship in the old Greek thought experiment that belongs to the hero Theseus. Over the years, each plank of the ship is replaced, one by one, as the old wood rots and new timber takes its place. Eventually, every piece of the original vessel has been swapped out. The question, famously, is whether the result is still Theseus's ship. The same shape, the same function, entirely new material. Now imagine a version of this question that does not unfold over years of gradual replacement, but instead arises from the structure of a closed time-like curve. Imagine that you are on such a curve. Your world line traces its path through space-time, carrying your body, your neurons, your memories, your sense of who you are, and then it closes. It returns to the same event, the same configuration, the same neural state, the same you, not a copy, not a twin. The same physical system arriving at the same point, with the same atoms in the same positions and the same electrochemical patterns firing across the same synaptic gaps. Is this a second time, or is it the same time? The question seems almost meaningless, and yet it presses against something we care about deeply, the idea that identity requires continuity, that you are who you are because of the unbroken thread of experience linking your present self to your past self. The philosopher Derek Parfit spent much of his career arguing that this intuition, however strong, may be misguided. What matters for personal identity, Parfit suggested, is not some metaphysical thread of continuity, but rather psychological connectedness, the presence of memories, intentions, personality traits, and experiential patterns that relate one moment of a person's life to another. On a closed time-like curve, all of these connections are preserved. Your memories at the beginning of the loop are exactly what they would be. Your personality is intact. Your sense of self is continuous and unbroken. And at the closing point, if we can even call it that, your psychological state is identical to what it was at the start. Parfit's framework would likely say, you are the same person. But here is the deeper strangeness. On a closed time-like curve, the question of whether this is the first time or the 100th time has no answer. The loop does not count its passes. It does not accumulate. It simply is, a single closed shape in space-time, containing a single continuous experience that happens to curve back upon itself. There is no second time because there is no mechanism within the loop to distinguish one traversal from another. The experience is singular. The shape is singular. You are not living the same day over and over. You are living a day that, in a geometric sense, curves, and you within it are simply you. Not again, not still, just you, held within a shape that happens to close. Nearly 4 centuries ago, René Descartes sat beside a fire and posed one of the most enduring questions in the history of thought. How, he asked, can I be certain that I am not dreaming right now? The warmth of the fire, the texture of his dressing gown, the clarity of his thoughts, all of these, he reasoned, could be faithfully reproduced in a dream. There was no sensation, no perception, no internal signal that could definitively distinguish waking life from a sufficiently vivid dream. Descartes used this observation not to claim that he was dreaming, but to establish something more fundamental, that the distinction between certain states of experience may be real and yet undetectable from within. The closed time-like curve presents a strikingly similar dilemma, though one that Descartes could never have imagined. If your world line is closed, if the path you trace through space-time curves back and forms a loop, then your experience, as we have explored, would be indistinguishable from that of a person on a linear world line. Your memories would feel sequential, your future would feel open, your sense of forward motion through time would be as vivid and convincing as it has ever been. No experiment you could conduct, No observation you could make, no thought you could think would reveal the loop. Not because the loop is hidden behind some barrier you could, with sufficient cleverness, overcome, but because the loop, by its geometric nature, does not produce any observable difference from within. The distinction between a closed world line and an open one is real, geometrically, mathematically, unambiguously real, but it is a distinction that can only be perceived from outside the system, from a vantage point that no entity within spacetime can occupy. This is an epistemological limit, not a gap in current knowledge that future science might fill, but a structural feature of the situation. Some truths about the universe may be true and forever beyond the reach of experience. This is not, perhaps, as unusual as it first sounds. Physics already contains quantities that are real but unobservable from certain perspectives. The absolute velocity of an object, for example, has no meaning in relativity, only relative velocity does. The total information content of a system behind a black hole's event horizon is by definition inaccessible to outside observers. The universe, it seems, is comfortable with truths that are beyond verification from particular vantage points. What the closed, time-like curve adds to this pattern is a peculiarly intimate dimension. The unverifiable truth is not about some distant object or abstract quantity. It is about the shape of your own life, the geometry of your own passage through existence. You may be on a loop, you may not, and no amount of introspection, measurement, or scientific inquiry conducted from within your experience can settle the question. Perhaps there is a strange peace in that, not knowing whether the road curves or continues, and recognizing gently that the not knowing changes nothing about the texture of the journey. Drop a coffee cup from a table. It shatters, the pieces scatter, the coffee pools on the floor. Now imagine watching this event in reverse, the liquid gathering itself, the shards leaping upward, the cup assembling on the tabletop, whole and steaming. You would know instantly that the film was running backward, not because any single law of physics was violated in the reversed version, but because the event played in reverse contradicts something deeper, the overwhelming tendency of the universe to move from order toward disorder, from concentrated energy toward dispersal, from low entropy to high. This tendency is called the second law of thermodynamics, and it is perhaps the most robust, most universally observed principle in all of physics. It gives time its direction. It is the reason the past looks different from the future. It is, in the language of physicists, the arrow of time. Without it, the equations of physics are almost perfectly symmetric. They work equally well forward and backward. It is entropy, and entropy alone, that breaks this symmetry and grants time its one-way character. But now consider a closed time-like curve. On a CTC, a system that begins in a particular state must, after following the loop, return to that exact state. The beginning and the end are the same event. This means that if entropy increased along part of the loop, it must decrease along another part, because the system must arrive back where it started, in the same condition, with the same degree of order. The arrow of time, on a closed curve, cannot point in one direction forever. It must at some point reverse, or perhaps more accurately, the very concept of a persistent direction becomes uncertain when the path is a circle. Some physicists have suggested that entropy on a CTC might increase locally, in any small segment of the loop. The second law would hold, things would decay and disperse, but globally, over the full circuit, the total entropy change would be zero. The arrow would exist in pieces, pointing forward along each section, but the circle as a whole would have no net direction. Others have argued that the presence of CTCs might require entirely new thermodynamic principles, frameworks that do not yet exist, built for a geometry that our current understanding of entropy was never designed to address. What is clear is that the relationship between entropy and closed time-like curves remains genuinely unresolved. The second law, which seems so absolute, so final, so embedded in the fabric of experience, meets a geometry that asks, what if the fabric curves back? And in that meeting, the arrow wavers, not broken, but no longer quite so certain of where it points. It is easy to misunderstand what Kurt Gödel was doing in 1949. The popular summary, that he discovered time travel is possible, captures something of the flavor but almost none of the substance. Gödel was not interested in travel. He was not imagining ships or passengers or voyages to the past. He was making an argument about reality, and to understand that argument, you have to understand the way Gödel thought about the relationship between mathematical structures and the world they describe. General relativity is not merely a tool for calculating how planets orbit or how light bends near stars. It is in the deepest sense a theory about the structure of spacetime itself. The field equations describe which geometries are possible, which shapes the universe is allowed to take, and every valid solution to those equations represents a universe that is, according to the theory, physically permissible. Not all of these solutions correspond to our universe. Some describe empty spacetimes, some describe universes with exotic matter distributions, and one, Gödel's, describes a universe filled with rotating matter in which closed time-like curves exist everywhere. Gödel's philosophical argument rested on a subtle but powerful observation. If the passage of time, the flowing quality of the present moment moving from past into future, were an objective, fundamental feature of reality, then it should appear in every valid solution to the equations that describe reality. A feature that is truly intrinsic to the structure of the universe cannot be present in some solutions and absent in others. But Gödel's solution contains no flowing present. It cannot, because in a universe threaded with closed time-like curves, there is no global ordering of events into past, present, and future. The loop makes such ordering impossible. Therefore, Gödel argued, the flowing present is not intrinsic. It is not a feature of reality as described by general relativity. It is something else, perhaps a feature of our particular universe's geometry, perhaps a feature of our minds, perhaps something even more elusive, but it is not fundamental. This argument was aimed directly at Einstein, who, despite having revolutionized the understanding of time, still seemed to hold that some form of temporal passage was real. Gödel was saying, your own theory, followed to its logical conclusions, disagrees. The equations you wrote do not require time to flow. They permit universes where the very concept of flow is meaningless. And if the concept of flow is not required by the physics, then the experience of flow, that sensation we all carry, that the present moment advances, that the past is gone and the future approaches, must originate from somewhere other than the fundamental structure of the world. Gödel never fully elaborated where he thought the experience came from. He left the argument at the edge of the cliff and stepped back. But the cliff remains, and the view from it, if one is brave enough to look, is breathtaking and vertiginous in equal measure. There is a way of thinking about the universe that, once encountered, is difficult to entirely set aside. Philosophers call it Eternalism. Physicists sometimes call it the block universe, and its central claim is simple, even if its implications are not. Past, present, and future all exist. Not sequentially, not one replacing the other like frames in a film. All of them simultaneously as a single four-dimensional structure, a block of space-time that contains every event that has ever occurred and every event that ever will. In this view, the moment of your birth is not gone. It exists at its coordinates in the block, as real and as present as the moment you are experiencing right now, and the moment of your last breath, wherever it lies in the geometry, exists as well. You do not move through the block. You are a shape within it, a world line extending from one set of coordinates to another, with every moment of your life equally real, equally present, equally there. This is not a fringe position. Many physicists and philosophers of physics regard eternalism as the most natural interpretation of relativity. The theory makes no distinction between past, present, and future. It treats all moments as equally valid points in a four-dimensional manifold. The special status we give to now, the feeling that this moment is the real one, that the past has faded and the future has not yet arrived, has no counterpart in the mathematics. It does not appear in the equations. It is, from the perspective of the theory, an addition that we bring to the picture, not something the picture contains on its own. Closed time-like curves make eternalism almost viscerally real. If a world line can revisit an earlier event, that event must still exist to be revisited. It cannot have faded. It cannot have vanished into a metaphysical past. It must be there, in the block, as solid and as accessible as any other point. The loop does not create the persistence of past events, but it makes that persistence undeniable. And this brings us to a feeling that is hard to name. If every moment of your life already exists, if the laughter you shared last week and the silence of next Thursday morning are both woven into the same structure, then you are not a fleeting point of awareness drifting through a vanishing present. You are a completed shape, a sculpture in 4 dimensions. Every version of you that has ever been, and every version that will be, exists right now in the block, not waiting, not fading, simply there. It is a strange form of comfort, perhaps, or a strange form of vertigo, or both at once. Close your eyes for a moment and try to feel time. Not to think about it, to feel it. There it is, a sensation of movement, of passage, of something flowing past you, or flowing through you, or carrying you along. The present feels like it advances. Moments arrive, are briefly vivid, and then recede into the past. The future feels like it approaches. This is perhaps the most universal and most intimate human experience, the sense that time flows. And in 1908, a philosopher named John Ellis McTaggart published an argument that this experience, however vivid, may not correspond to anything real. McTaggart distinguished between 2 ways of ordering events in time. The first, which he called the A series, assigns to every event a position in the categories of past, present, and future. This morning's breakfast is past. This sentence is present. Tomorrow's sunrise is future. The A series is dynamic. Events move through these categories. What was future becomes present, then past. The second ordering, the B series, arranges events only in terms of earlier and later. Breakfast is earlier than this sentence. This sentence is earlier than tomorrow's sunrise. The B series is static. Nothing moves, nothing flows. Events simply stand in fixed relations of before and after. McTaggart argued that the A series, the flowing version of time, is logically incoherent. For an event to be past, present, and future requires it to have contradictory properties simultaneously. The usual response, that it has these properties at different times, is circular, because it uses the concept of time to explain time. The argument is intricate and has been debated for over a century, but its core suggestion is striking. What we experience as the flow of time may have no objective counterpart. The B series, the static ordering, the world of earlier and later with no advancing present, may be all there is. Physics, remarkably, seems to lean in the same direction. The equations of general relativity do not contain a mechanism for the present to move. There is no variable in the theory that corresponds to now. The block universe sits there, all of its moments equally real, and no physical process carries a spotlight from one to the next. Closed time-like curves reinforce this absence. On a closed curve, the very idea of an advancing present becomes incoherent. Advancing toward what? The future, on such a curve, circles back to the past. There is no forward direction that extends indefinitely. There is only the curve, a static shape, existing all at once, containing a sequence of experiences that feel, from inside, like flow. Perhaps the river of time is not a river. Perhaps it is more like a landscape, hills and valleys stretching in every direction, experienced sequentially by a creature who can only perceive one point at a time. The river was never there, only the walking, only the view from wherever you stand, and the quiet, unknowable question of whether the landscape continues where you cannot see. We have travelled a considerable distance tonight, through geometries that curve, through paradoxes that unsettle, through the invisible interior of a loop and the philosophical dismantling of a river. And now, gently, let us return to the title. You have already lived tomorrow. At the beginning, those words may have felt strange, unsettling perhaps, or deliberately mysterious. But now, having followed the logic of closed time-like curves and the philosophy of the block universe, we can hear them differently, not as a riddle, not as a paradox, but as something closer to a description. If eternalism holds, if all moments exist as coordinates in a four-dimensional block, then tomorrow is not something that has not yet happened. It is something that exists at a particular location in the structure of spacetime, a place in the truest geometric sense that you have not yet visited. The way a city on the far side of a continent exists right now, even though you are here and it is there, you will arrive. The city is not rushing toward you. It is simply waiting in its place, being what it is. Tomorrow, in this view, is the same kind of thing. It exists. It has its shape, its events, its qualities. It does not depend on your arrival to come into being. It is already there, patient, quiet, complete. And a closed time-like curve is simply an unusual path through this landscape. Most world lines in spacetime move through the block in one direction, visiting each moment once, in order. A closed time-like curve revisits. It takes a path that curves through the terrain and returns to a region already traversed. Not because time has reversed, but because the geometry allows for routes that loop. The traveler on such a curve has not broken any law. They have simply taken a road that bends back through terrain they recognize. The title, then, "You Have Already Lived Tomorrow," is not about repetition. It is about the pre-existence of the places you will go. Tomorrow is not being created by the passage of time. It is not assembled, moment by moment, from the raw material of the present. It is there, in the block, at its coordinates, waiting, if waiting is even the right word for something that does not experience duration from the outside. And there is something in this idea, something we will explore more fully as we approach the end of this journey, that begins to feel less like vertigo and more like a kind of rest. If tomorrow already exists, then you do not need to build it. You do not need to worry it into being. It is there, and it will still be there when you arrive. You can close your eyes. You can let go of the anxious sense that the future must be constructed by effort or vigilance. The landscape does not disappear because you stop watching it. The rooms ahead of you in the block do not cease to exist because you have not yet entered them. They remain, quiet, ready, already shaped, already real. In 1992, Stephen Hawking published a paper with a title that was, by the standards of theoretical physics, unusually playful. He called it Chronology, Protection, Conjecture. The word conjecture is important. It signals that what Hawking proposed was not a proven law, but an educated guess, a carefully reasoned suspicion about how the universe behaves. His suspicion was this, that the laws of physics, when fully understood, conspire to prevent the formation of closed time-like curves. Not gently, not as a preference, but absolutely, as a fundamental prohibition woven into the structure of reality. Hawking's reasoning drew on quantum field theory. He argued that as a region of space-time approaches the conditions necessary to form a CTC, as the geometry bends closer and closer to closure, quantum effects would grow catastrophically. Vacuum fluctuations, those tiny restless energy oscillations that permeate empty space, would be amplified by the curving geometry until they generated a wall of energy dense enough to destroy the developing CTC before it could fully form. The loop, in essence, would be burned away by the very quantum fields that inhabit the space-time around it. Nature would intervene, Hawking suggested, not through a visible barrier but through an escalating instability that makes the final step toward closure impossible. He summarized the idea with characteristic wit, remarking that the best evidence against time travel was the absence of tourists from the future. It was a joke, but it carried a serious point. If closed time-like curves were physically realizable, why had no evidence of their use, no signal, no visitor, no anomaly ever been detected? But here is the crucial caveat. Hawking's chronology protection remains, more than 3 decades after its proposal, unproven. It is supported by certain calculations in sex-molecular gravity, a framework that blends general relativity with approximate quantum corrections. But sex-molecular gravity is known to be an incomplete theory. It breaks down precisely in the regimes where chronology protection would need to operate, the extreme conditions near the formation of a CTC. To truly settle the question, One would need a complete theory of quantum gravity, and no such theory yet exists. So Hawking's conjecture stands as something between a prediction and a hope. An elegant, plausible, widely respected hope, but a hope nonetheless. The universe may protect the order of time, or it may not. And the honest position, the one that does justice to the state of our knowledge, is to hold both possibilities gently, without insisting on either. While Hawking was arguing that the universe might forbid closed time-like curves, another physicist was asking a very different question. David Deutsch, a pioneer of quantum computing and a proponent of the many worlds interpretation of quantum mechanics, wanted to know what would happen if you treated a closed time-like curve not as a paradox to be prevented, but as a resource to be used. Deutsch's 1991 model approaches CTCs from the perspective of quantum information. In the many worlds framework, every quantum measurement does not produce a single outcome, it produces all possible outcomes, each realized in a different branch of an ever-splitting reality. A particle that can be spin up or spin down is, before measurement, both, and after measurement, it is spin up in one branch and spin down in another. When Deutsch applied this framework to closed time-like curves, the paradox is dissolved. The grandfather paradox, for instance, loses its teeth. A traveler who follows a quantum CTC into the past does not interact with their own history. They interact with a different branch, a version of the past that is consistent with their arrival but that belongs, in a sense, to a parallel history. No contradiction arises because the traveler's actions affect a branch they were never originally part of. The loop closes without paradox because each pass around the curve engages with a different strand of the quantum multiverse. But Deutsch's model revealed something even more surprising than paradox resolution. He showed that a quantum computer with access to a closed time-like curve could solve computational problems that are believed to be intractable for any ordinary computer. Problems classified as NP-complete, problems where verifying a solution is easy but finding one is, for all known methods, prohibitively slow, could be solved efficiently. The CTC in Deutsch's model effectively allows the computer to consult the results of computations it has not yet performed. The loop becomes a shortcut through computational difficulty. Time, curved back upon itself, becomes a tool for solving problems that the forward-flowing universe cannot crack in any reasonable time frame. This is a profound shift in perspective. Closed time-like curves, in Deutsch's vision, are not errors in the fabric of space-time. They are not loopholes to be sealed or paradoxes to be feared. They are capabilities, features, not bugs. Doors through which information can pass in ways that amplify the power of computation beyond anything the linear flow of time permits. Whether Deutsch's model describes physical reality is, of course, open. It depends on the many worlds interpretation, which itself remains debated. But the model demonstrates something important regardless: that the relationship between time, information, and possibility is far more intricate than our everyday experience suggests. Even if closed time-like curves are mathematically permitted and logically manageable, there remains a quieter barrier, one that involves not the structure of equations, but the substance of the physical world. To build a traversable wormhole of the kind Kip Thorne and Michael Morris described, you would need exotic matter. Specifically, you would need matter with negative energy density, a substance that, in a certain precise sense, contains less energy than empty space itself. This sounds impossible. In ordinary experience, energy is always positive. A hot cup of tea has more energy than a cold one. A moving ball has more energy than a stationary one. Empty space, one might think, represents the baseline, zero energy, the starting point from which all quantities ascend. But quantum mechanics complicates this picture. Between two closely placed metal plates, in a phenomenon called the Casimir effect, the vacuum energy is slightly lower than in the open space outside the plates. The plates restrict which quantum fluctuations can exist between them, and this restriction creates a region where the energy density is, relative to the surrounding vacuum, negative. The effect is real, it has been measured. The plates are drawn together by the imbalance, and the force between them matches theoretical predictions with impressive accuracy. So negative energy density exists. It is not fantasy, but the Casimir effect operates at the scale of micrometers. The amount of negative energy involved is inconceivably small. To hold open a wormhole large enough for anything meaningful to pass through, even something as modest as a single photon, would require quantities of exotic matter that exceed, by many orders of magnitude, anything that quantum effects have ever been observed to produce. Some physicists have explored whether quantum inequalities, fundamental limits on how much negative energy can exist in a given region for a given duration, might be the universe's way of setting a ceiling. These inequalities, derived from quantum field theory, suggest that the more negative energy you try to concentrate, the shorter the time you can sustain it. There may be a built-in limit, a cosmic rationing of the exotic substance that CTCs require. This is different from Hawking's chronology protection. It is not a dramatic intervention, not a wall of energy rising to destroy the loop. It is something quieter, a scarcity, an absence of the raw material needed to build the structures that would allow time to close. The universe in this picture does not need to actively forbid closed timelike curves. It simply declines to provide the ingredients. A recipe that is theoretically valid, a set of instructions that the mathematics endorses, but a pantry that is almost entirely empty. Whether this scarcity is absolute or merely reflects our current understanding is, like so much in this territory, genuinely unknown. We have arrived, in this journey, at a place that deserves honesty above all else. The question of whether closed timelike curves can physically exist, not as mathematical objects on paper but as actual features of the spacetime we inhabit, rests on a foundation that is, at this moment in the history of physics, cracked. On one side of the crack stands general relativity. It is a theory of gravity, of spacetime geometry, of how mass and energy shape the universe. It has been tested with extraordinary precision. It predicted the bending of starlight, the existence of gravitational waves, the behavior of clocks at different altitudes. It has never been observed to fail within its domain, and it permits closed timelike curves. On the other side stands quantum mechanics. It governs the behavior of particles, of light, of the fundamental forces that hold atoms together. It too has been tested with extraordinary precision. It has predicted the behavior of electrons, the spectrum of hydrogen, the strange entanglement of distant particles. It has never been observed to fail within its domain, and it may, through mechanisms like Hawking's chronology protection or the scarcity of exotic matter, forbid closed timelike curves. The problem is that these two theories do not speak the same language. They describe overlapping aspects of the same universe using fundamentally different mathematical frameworks. And in the extreme conditions where CTCs would form near singularities, at the Planck scale, in the deep interiors of rotating black holes, both theories claim jurisdiction, and neither can be fully trusted. What is needed is a theory of quantum gravity, a single framework that unites general relativity and quantum mechanics into a coherent whole. Such a theory would, among many other things, settle the question of closed timelike curves once and for all. It would tell us whether the permission granted by general relativity survives the constraints of quantum mechanics, or whether the loops are forbidden at the deepest level of physical law. But no complete theory of quantum gravity exists. String theory, loop quantum gravity, causal set theory, these are active research programs, each offering partial insights, each incomplete. The question of CTCs lives exactly at the fracture between our two best descriptions of reality, not in the territory where either theory speaks with confidence, but in the gap between them. This is not failure. It is the frontier, the place where physics has not yet spoken clearly, and there is perhaps something calming about recognizing a genuine boundary of knowledge, not a boundary of laziness or ignorance, but a boundary of honest uncertainty. The universe holds this answer. We have not yet learnt to hear it. But the question is being asked, quietly, by some of the most careful minds in the world. And the crack in the foundation, uncomfortable as it may be, is precisely where the light of future understanding will eventually enter. Let us sit, for a moment, with a simple and remarkable fact. The most rigorously tested theory of gravity ever devised, a theory that has survived every experimental challenge for more than a century, permits time to close upon itself, not in a hidden, reluctant way, not as an obscure edge case buried in exotic mathematics, but in multiple independent solutions arising naturally from the geometry of rotating matter, spinning black holes, and curved spacetime. The permission is broad, it is robust, and it persists. One might expect such a permission to be easily dismissed if closed time-like curves seem so strange, so contrary to experience. Surely there is some mechanism that rules them out. But as we have seen, the mechanisms proposed, chronology protection, exotic matter scarcity, quantum instability, are conjectures, not conclusions. They are plausible suggestions, not proven prohibitions. The permission, as of now, remains unrevoked. And this matters even if no closed time-like curve is ever observed, because a theory's permissions reveal the shape of reality as surely as its prohibitions. When general relativity forbids faster-than-light travel through flat spacetime, that prohibition tells us something real about the universe's structure. And when the same theory permits world lines that close, that permission also tells us something real, something about what the geometry of spacetime allows, something about the relationship between time and curvature, something about the limits of linearity. If time can, in principle, form loops, then the linear, forward-flowing quality of our temporal experience is not a necessity. It is a feature of our particular situation, our particular location in spacetime, our particular geometry, our particular cosmic history. Linearity is local. It may even be typical, but it is not compulsory. This is perhaps the quietest and most lasting insight from the entire study of closed time-like curves. Not that time travel is possible, that framing is too narrow, too tied to machines and voyages, but that time itself, the fabric we move through, the structure that orders our experience into before and after, is more flexible than it appears. It can curve, it can close, it can, in the right geometry, bring tomorrow and yesterday into contact. Whether it does so in our universe, in our region of space-time, remains an open question, but the permission is real, and the fact that such a permission exists, that the deepest mathematics of gravity allows it, invites a particular kind of humility. We may think we know what time is. We may feel its passage so vividly that we mistake the feeling for the thing itself. But the equations, quietly, persistently, keep reminding us that the universe is under no obligation to match our intuitions. It is larger, it is stranger, and it holds its possibilities gently, without hurry, without resolution, without needing us to understand them before they can be true. There is a particular kind of anxiety that visits in the dark hours, a feeling that tomorrow is uncertain, unformed, dependent on forces you cannot control, that the future is a blank space waiting to be filled by effort, by worry, by the ceaseless work of anticipation. We carry this feeling so habitually that we rarely question its premise, that tomorrow does not yet exist, that it must be made, that without our vigilance it might not arrive at all. But tonight we have followed a thread that leads to a different possibility. If the mathematics of general relativity is to be trusted, if the block universe describes something real about the structure of existence, then tomorrow is not blank, it is not unformed, it is not waiting to be built, it already exists. Not as a prediction, not as a probability, but as a location in the geometry of space-time, as real and as present as the place where you are lying right now. The events of tomorrow, whatever they may be, have their coordinates. They occupy their place in the block. They are not rushing toward you. They are not contingent on your readiness. They are there, quiet, patient, complete. And if this is so, then the anxiety of anticipation rests on a misunderstanding, not a moral failure, not a weakness. A misunderstanding, the very human, very understandable assumption that the future is made by the passage of the present. That time must carry you there, that without motion, without effort, without the feeling of progress, you will not arrive. but you will. The block does not require your effort to contain its future regions. The landscape does not need you to walk toward it in order to be real. It is already there, all of it, including the morning that will follow this night, including the light that will eventually return to the room where you are resting now. There is something almost tender in this idea, a gentleness to the notion that the future is not fragile, that it does not depend on your wakefulness, that even as you drift, even as your thoughts grow soft and unfocused, tomorrow holds its shape. You do not need to guard it. It is already complete. If the block universe is real, if every moment persists at its coordinates in four-dimensional spacetime, then something follows that is easy to state and strangely difficult to feel. Nothing is lost, not truly. The morning you spent last week watching rain slide down a window, it is still there, at its location in the block. The sound of someone's voice speaking your name 6 months ago, it exists at its coordinates, as real and as present as any moment in the structure. The laughter of a conversation that ended hours ago has not vanished. It has simply been visited and moved past. It remains. The closed time-like curve, in this context, adds an unusual dimension to this permanence. On a linear world line, the persistence of past moments is theoretical, a feature of the block that you cannot return to experience. But on a CTC, the persistence becomes navigable. A world line that closes can revisit, not in the sense of memory or nostalgia, but in the actual geometric sense of arriving again at coordinates already passed through. The moments are not merely preserved, they are in principle reachable. We do not know whether our world lines are closed. We have explored the reasons why this question may be unanswerable from within, but the underlying picture, the persistence of moments, the idea that the past does not dissolve but remains, does not depend on CTCs. It follows from the broader framework of the block universe, which is itself supported by some of the most well-tested physics ever developed. There is a consolation here that has nothing to do with technology or possibility. It is simply the quiet suggestion that the moments you have loved are not gone. They exist, perhaps not in any way you can access, perhaps not in any way that makes practical difference, but they exist, in the structure, at their place, holding their shape. The block does not forget. And on a night like this, when the day behind you is fading and the day ahead has not yet been experienced, there may be comfort in the thought that neither the fading nor the not yet diminishes what is real. Everything you have lived persists. Everything you will live already holds its place. And you, here, in this quiet moment between them, are simply resting at one point along a shape that contains all the others. Your body knows something about return. Every 24 hours, give or take, it cycles back to a familiar darkness. Melatonin begins to rise as the light fades, produced by the pineal gland in response to signals from the suprachiasmatic nucleus, a tiny cluster of neurons behind your eyes that has been keeping time since before you were born. Cortisol, the hormone of waking alertness, dips toward its daily minimum. Your core body temperature drops slightly. Your brain begins to shift its electrical patterns, moving from the fast, focused rhythms of wakefulness toward the slower, deeper oscillations of sleep. This happens every night. Not identically, there are variations, fluctuations, the gentle noise of a biological system responding to a changing world. But the overall pattern is remarkably consistent. A cycle, a curve that returns. The same neurochemical landscape, visited again and again, as reliable as any astronomical orbit. In a sense, your circadian rhythm is the most intimate closed curve you will ever experience. Not a closed time-like curve in the geometric sense. The physics is different, the structure is different, the implications are different, but the shape rhymes. The return to a familiar state, the feeling of arriving, each night, at a place you have been before. The darkness that is not new darkness but the same darkness, metabolically and hormonally, that you have visited thousands of times, and tonight is no different. Your body is doing now what it has done on so many other nights, gathering itself, quieting its systems, preparing to return to the neurochemical signature of rest. The melatonin is rising, the alertness is fading, the temperature is falling. You are, in the language of biology, approaching the familiar coordinates of sleep. There is nothing you need to do to assist this process. The suprachiasmatic nucleus does not require your conscious participation. The cycle turns on its own, as it has turned since the earliest days of your life, as it will continue to turn for as long as your body draws breath. You are not falling asleep. You are returning to sleep, arriving, once more, at a place your body already knows. A small, biological loop. A curve that closes gently, every night carrying you back to the same quiet shore. The room around you is still. The sounds of the day have thinned to almost nothing. And here, in this quiet, we arrive at the simplest version of everything we have explored tonight. Time, perhaps, is not what it seems. It may not flow. It may not advance. It may not carry you from one moment to the next the way a river carries a leaf. Instead, it may be something more like a landscape, vast, quiet, already complete, a structure in which every moment exists, not waiting to be reached, but simply being where it is, and you are within it, not racing through it, not clinging to the present as it slips away, simply resting at one set of coordinates in a geometry that holds all the others. Tomorrow is there. It has always been there, not as a threat, not as an obligation, not as something you must prepare for or worry into existence. It is there the way a meadow is there on the far side of a hill, present, patient, undisturbed by whether you have arrived yet. You have already lived tomorrow, not because time has played a trick on you, not because reality is broken or strange, but because in the deepest picture that physics has yet offered, the moments of your life are not created and destroyed in sequence. They persist, they coexist, they are held, all of them, in a structure that does not hurry and does not forget. And if that is so, then there is nothing you need to do right now except rest. The morning will come, not because you summoned it, not because you stayed awake to watch for it, but because it is already there, at its coordinates, holding its shape, gentle and undisturbed. The light will return. The world will resume its familiar patterns, and you will arrive at tomorrow the way a traveller arrives at a place that was always on the map, not surprised, not anxious, just arriving. For now, let the thoughts settle like something warm laid over you. Time is a shape, you are held within it. Tomorrow already exists, and it is kind, and the curve of this night, this small familiar return to darkness, is carrying you, gently, toward a morning that has been waiting for you all along. You are already home,